My name is Victoria Brown, and this is Lab 4 Magnetic Braking. The purpose and goals of this experiment are to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare our computational predictions with our observed data. The main findings throughout this experiment are our experimental results. We had 1.73 seconds. And when using our computational method, it was 1.95 seconds for the magnet to reach the end of the tube. So some fundamental principles we will discuss throughout this lab is Beer-Savart law, Faraday's law, and Newton's second law. And you can pause to read the descriptions of each one of these, as these will be helpful as we continue our conversation. For our models, we have a computational model, which will be using glow script coding, and we also have our experimental model, which is going to be aluminum foil and a bar magnet. Per the lab instructions, the system is going to be the bar magnet and the aluminum foil. The surroundings are going to be everything else. In our initial conditions, we have to have our bar magnet being representative of a magnetic dipole. For our methodology, we're going to have to mark the north pole of the bar magnet using our app, and then we are going to drop the bar magnet into the aluminum foil tube. We will then measure how long it takes for the bar magnet to exit, and then we will repeat this 5 times to get an average. It is assumed that air resistance is negligible. The bar magnet is going to be a magnetic dipole and treated as such, and the aluminum foil acts as a conductive and non-ferrous tube. Some observations from our experimental model. We had our measurements seen on the left side using the mu from our lab 2, which is 1.74. And on the right, we can see our observations from each trial, averaging about 1.73 seconds. Here's some of my code using our computational model. And so on the left, we have where we created the tube in our code. And then on the right, we actually create the bar magnet and set up our initial conditions. Here on the left, we have our code to represent the magnetic flux, and then on the right shows our final product, in which you can see the tube at the top that has been created, and then the graph represents the velocity versus time, and then at the bottom we can also see that the time in the tube is 1.953 seconds. So here is a variety of questions that pertain to the simulation. And so in terms of interpretation, we have to understand color coordination in terms of the current. And so due to Lenz's law, the blue is going to be clockwise. Blue is what you can see on the previous slide. And the red is going to be counterclockwise, which is not seen. And then if you flip the magnet around, we're going to have it going in the opposite direction. So we also compare the time between our experimental and computational models. So we have, again, that 1.73 seconds versus the 1.953 seconds. And it can be assumed that the computational system is more accurate because it does have more trials, as there are more embedded loops. And then when looking at the chart that was also seen on the previous slide, at around 0.2 to 1.8 seconds, the forces become balanced, and you can see that from the flat line that was shown. With this experiment, there's a lot of room for error, such as an incorrect mu value from the previous lab, as well as an error in timing. So these are the 2 questions that we are asked, what if? And so we look at the conductor and resistivity reduction, and so the magnet is going to essentially in this scenario fall slower. as there's going to be an increased counteracting force against gravity. And then we're also asked, what if there were holes in the tube? And so this impact would cause the magnet to ultimately fall faster, as the magnetic force is going to decrease from the reduced ring current. Thank you.